Alrighty, let's prove that f the derivative of ln of x is 1 over x. So I'm going to do it two ways. One is going to be just straight up definitional derivative, and then the second way is going to be way much easier than that. So let's just get the whole thing out of the way. I really don't like using definitional derivatives, but in order to prove it, we have to use it. It sucks, but let's just get that out of the way first. Okay, so let's plug it into the, we'll call it method 1. Let's just call it method 1. Method numero uno. So, obviously the definition derivative is just the limit as, not x, my fault, as h reaches 0, that is ln, and then x plus h minus ln of x over h. Now, all we do, we just solve until we don't have h anymore. So first thing we can do is that we can just rewrite that using and make it a little bit make it a little bit more easier to use. So we're gonna write this as the limit of h to 0. Now we're gonna use logarithmic properties, which make it easier. Instead of writing it over h, I'm just gonna write it as times 1 over h, so it'll be a little bit easier to to solve. So now we can just do natural log of x plus h over x. Now it's way more easier to look at. X and x will just make 1, so it'll just be h over x. So this would just equal the limit of h to 0, 1 over h, ln, and then 1 plus h of x to the h power. Now, this looks mighty familiar to a certain number, you could say, which is e. So, e, right over here, e is equal to the limit, let's just use t on it, to infinity as, it's not ln, my fault, it's not ln, it's 1 plus 1 over t to the t power. That's how you get e. And that's very important because this looks mighty familiar to it. Also, that's not supposed to be there. It's supposed to be 1 over h. I got ahead of myself because obviously to quickly fix that error, 1 over h goes to logging because in logarithmic identities, a ln b is equal to the natural log of b to the a power. That's why we did that. That was my bad. I'm sorry I didn't see that. So now this looks mighty familiar to that property over there, right? So let's do some substitution. Let's make u equal to h of x, right? This is important, so I'm gonna circle it because it's pretty important. Alright, let's do some manipulation right here. H equals u of x, right? Basic algebra. 1 over h equals 1 over u of x, right? Which is also equal to 1 over h times 1 over x, right? That's pretty important. So when we put it into the u form, that'll be very important to use. We know that h approaches 0, right? So we want to find out what u approaches. We know that h is 0, so 0 over a number, unless it's not 0, is 0. Luckily, the natural log of x doesn't approach 0 when you draw a graph of it, right? It never approaches x. So we are very lucky that x can't be less than 0. So obviously that'll have to mean that u also equals 0 because 0 divided by anything greater than 0 is 0. So that's taken care of, right? So now we can rewrite it into form that we wanted to write it in. So let me use blue again. So now we can rewrite it as a limit as u approaches 0 and then we just replace everything with u. So natural log 1 plus 1 over u to, what's it, 1h times 1 over x, right? That's how you do that, right? Now we can do some manipulation. Limit u to the 0 is equal to natural log, let's do double parentheses 1 plus 1 to the u, 1 to the h, and then 1 to the x, right? Cool. So we can bring the 1x down in front of the limit. You'll see why. Okay. We can bring this limit inside the natural log, because everything that we're gonna find the limit is inside the limit, which will make it way more easier to solve. So let's just bring everything inside. Now, this looks mighty familiar to what E is, right? Also, I think it's supposed to be inside too. Right? Yeah, I think so. Okay, this looks mighty familiar, right? This is almost the same as that equation right there. So this would have to mean that it has to equal E. E and natural log cancels because, yeah, and which is just left with just 1 over x. There it is. That's one way to solve it. I probably made a couple of mistakes in there. I probably did, but hopefully I get the picture. Most likely I probably made a mistake somewhere here. I don't know if it's 1 over u because it doesn't make sense because why is h there? Right? But it's okay. That's one way to solve it. The second way is way more easier than whatever this is. I hate doing it like this. See, the problem with this is that I probably made a mistake on it, which is why I don't like using this. But this method is way more easier than doing this. So let's just move on to method 2. Should be way more easier, right? I'm even gonna write bigger. Method 2. So method 2 involves implicit differentiation, but this can literally be done in like 6 steps. It's like actually like kindergarten math right here. So let's make y equal to ln of x. We can cancel ln of x by raising everything here to the e power. So let's put e here, and then let's put e there. E to the y is just e to the y. Right? And then e and ln of course cancels out each other, which will just equal x. Then what we can do is that we can bracket everything here and implicitly differentiate it. E to the y, and then we have to put dy dx because we'll differentiate it with respect to x, so obviously chain rule, and then x will just be 1, right? We can divide this by e to the y. So dy dx equals 1 over e to the y. We know that e to the y is equal to x, so we can just rewrite that as 1 over x, and then there is our other proof right there. So this is probably like one of the 2 of the main ways you can get 1 over x. Again, this is a more like faster, convenient way, whereas the definition derivative is way more harder to explain. Well, I probably even made a mistake in it, but hopefully that proves that. So yeah, there it is. That's it. Thanks for watching. I hated that.